So, in this lecture we will continue with the topic of harmonic loading. We will solve some more examples on harmonic loading and then move on to understanding how to solve periodic but non-harmonic loading problem. So, let us move into the next example. So, this is the example of ground motion where we have a compressor which is supported on an isolator pad which is giving a stiffness of K, the value of K is given. Okay. A harmonic excitation of magnitude 200 Newton is applied to the system and the system is operating at a frequency of 100 radian per second. The phase difference between the excitation and the steady state response is 15 degree. We have to find out the damping ratio and the maximum deflection due to the excitation. So, let me write this, let me summarize this problem. So, we have mass m, which is equal to 25 kg. This is given for a single degree of freedom. The stiffness K is given as 5 into 10 to the power 5 Newton per meter. The amplitude of the force F t is given as 200 Newton into some cos omega t, that is acting on the system. So, then the frequency of the this omega is given as 100 radian per second. So, these are given. What we need to find out is zeta and x. The other thing that is given is the angle phi, which is given as 15 degree. Okay. So, the steady state response u t is going to be x into cos omega t minus phi. This phi is given as 15 degree. We need to find out this x as well as zeta, which is also needed to find out x. So, let us solve the problem. So, the first thing that we need to do is to see what are the natural frequencies of the system. So, let me find out the natural frequencies of the system. What is the, so let me find out the natural frequency. So, the natural frequency is omega n, which is root over k by m. So, we have seen that k is nothing but 5 into 10 to the power 5 Newton per meter. So, and the mass is 25 kg. So, if we evaluate this, we are going to get this as 141.42 radian per second. So, we know that the driving frequency which is omega is given as 100 radian per second. Okay. So, the frequency ratio therefore can be evaluated, which is going to be omega by omega n, which is 100 by 141.42, which is going to be 0.707. Now, we have seen earlier that the phase angle or the phase difference between the response and the forcing function is phi, and we have seen this relation that tan phi is nothing but 2 zeta omega by omega n divided by 1 minus omega by omega n square. So, this we have seen. So, now let us see what are the things that we know in this expression. We know phi. Phi is given as 15 degree, which can be converted to radian per second, which is 15 into 2 pi by 360 degree. So, I know that the left hand side is tan 15 degree. On the right hand side, I do not know zeta, but I know omega by omega n, which is 707 by 1 minus 0.707 square. And this, if we evaluate, this is going to give us the value. So, this I know tan 15. So, tan 15 is can be evaluated, and from this we can obtain the value by solving this equation in a very straightforward way. We can see that the value of zeta is going to be 0.0945. Okay. Therefore, one part of the problem is solved. So, I have seen that the damping factor is nothing but 0.945. So, now let me do the next part of the problem. So, the next part of the problem asks for finding out the steady state amplitude. So, we know that the steady state amplitude is going to be x, which is going to be the amplitude of the forcing function, which is given as 200 Newton by the stiffness k into h omega, the magnification factor. So, I need to find out the magnification factor first. So, let me find out the magnification factor, which is h omega, and that is equal to 1 by 2 zeta omega by omega n square plus 1 minus omega by omega n . So, here I know the value of zeta, which is 0.0945. I know the value of frequency ratio omega n, which is 0.707. So, if I plug in these values, I get the value of h omega as 1.932. Okay. So, once I know the value of h omega, I can directly evaluate this as 200 Newton. K is nothing but 5 into 10 to the power 5 Newton per meter into 1.932, which is going to be 0.7728 into 10 to the power minus 3. So, this is going to be in meter. So, I can write this as 0.7728 millimeter. So, this is the amplitude of the steady state response. So, that's all about the problem. So, let me go back to the next problem. So, here the problem states that there is a rotating machine which has a mass of 5 kg, and it is placed on an elastic foundation which has an equivalent stiffness. So, a 5 kg mass with an equivalent stiffness of 3 into 10 to the power 4 and with a damping factor of 0.04. So, the sensors indicate that the table on which the machine is placed vibrates at a frequency of 100 radian per second and an amplitude of 0.6 mm. So, we need to find out the steady state amplitude of acceleration, okay, not only displacement, but acceleration. Let me summarize the problem. The problem is that there is a table and a rotating device or a rotating machine with mass equal to 5 kg is resting on an isolator pad. So, the isolator pad has a stiffness of K, which is 3 into 10 to the power 4 Newton per meter, and a damping factor. So, there is a damper. The damping factor is given as 0.04, and it is said that we have placed sensor on the table and the sensor measure that this table itself is vibrating. It's having a response, it's having a displacement yt, which is 0.6 into 10 to the power minus 3 meter into some cos omega t, where omega is 100 radian per second. So, we have to find out. So, this response, the steady state response u t, can actually be written as x into cos omega t minus phi, and we need to find out x. So, that is the problem given here. So, we have done this problem, the theory of this problem earlier. We have seen that, so that x by a is called the transmissibility factor, we have done this earlier, and the equation for the transmissibility factor, the expression is given as 1 plus 2 zeta omega by omega n whole square root of that into the magnification factor, okay, where x is what we need to find out. A is nothing but 0.6 millimeter or 0.6 into 10 to the power minus 3 meter. Okay. So, this problem is a very steady state, very straightforward problem. We know zeta, we know omega by omega n, therefore, we can also find h omega. So, we have to just plug in the values here and get the expression for the transmissibility factor, from where we can find out x. So, let us quickly solve the problem and see what is the answer. So, what is the natural frequency of the system? So, the natural frequency is omega n, which is root over k by m, which is 3 into 10 to the power 4 by 5 kg. So, if we evaluate that, that is going to come to be 77.46 radian per second. Therefore, the frequency ratio, which is omega by omega n, the omega is given as 100 by 77.46, which is equal to 1.29. Okay. And we know that zeta is nothing but 0.04. 4. Therefore, we can find out the magnification factor. We already know the expression for magnification factor. I am not rewriting here. If we plug in this value into the expression, you will see that h omega will come out to be 1.48. Therefore, x is going to be 0.6 millimeter, that is 0.6 into 10 to the power minus 3 into 1.48 into 1 plus 2 zeta, that is 2 into 0.04 into omega by omega n, which is 1.29, the square root of this into the square of this and the square root of this. So, if you evaluate these numbers, you will get that the displacement that comes out is 0.893 into 10 to the power minus 3 meter, or 0.893 millimeter. So, this is the steady state amplitude. So, but the problem asks us to find out the steady state acceleration. So, we need to find out the steady state acceleration. So, we know that the steady state response is ut, which is x cos omega t minus phi. Therefore, the steady state acceleration is double derivative of that, which is minus omega square x into cos omega t minus phi. Therefore, the steady state acceleration, which I call as x subscript acceleration, is nothing but omega square into x, which is 100 radian per second is omega. So, omega square into 0.893. So, that comes out to be 8.93 in, that is in millimeter per second square. So, this is the answer of the problem. So, the third example that I have chosen is the example of a rotating unbalance. So, it is, as I said earlier, a rotary blade or a rotor is very common in an aircraft or in a helicopter. So, this is such an example where we have an aircraft, and on the tail region of the aircraft there is a rotor section. So, the rotor has 4 blades. Now, the total mass of the rotor system, that is the mass of the blade plus mass of the gearbox and the rotating machine is 33 kg, and it is rotating with a natural frequency of 150 radian per second. So, the damping ratio is also given as 0.05. Now, it is said that the rotor is rotating with an angular speed of 800 rpm. Now, what happens while the aircraft is flying, a foreign object of the mass of 0.75 kg gets stuck to one of the blade at a distance of 50 centimeter from the axis of rotation. Therefore, as the particles get stuck to one of the blades, there is a rotating unbalance, and as a result this whole rotary system or the whole rotor section is going to start vibrating. What we need to find is the steady state amplitude of the rotor system in the vertical direction due to this unbalance. So, let us summarize what we know. We know that the mass of the rotating section, the entire mass is 33 kg. The damping ratio is 0.05. the natural frequency omega n is 150 radian per second. We know that the driving frequency is 800 rpm, which can be converted easily to radian per second as 800 into 2 pi by 60, which is going to be 83.77 radian per second. And we know that the mass of the unbalance is 0.75 kg, and the unbalanced mass is at a distance of 50 centimeter or 5 meter from the axis of rotation, and we need to find out the amplitude of vibration. So, let us try to find out. So, we know that for a rotating unbalance, the equation of motion is going to be mu double dot plus c into u dot plus k of u is going to be m, mass of the rotating unbalance, e, the eccentricity or the distance from the axis of rotation, and omega square, where omega is the driving frequency, into sin omega t. So, how to solve this system? We have to just assume that the steady state solution is ut, which is x sin omega t minus phi. We have to substitute that into this equation and solve for x. If we solve for x, we will see that the rest x will be coming out as m into e into omega square by k into h omega, where h omega is the magnification factor. Instead of k, I can write as k can always be written as m into omega n square. So, this can be written as m into k into omega square by capital M into omega n square into h omega. Okay. So, out of this, what do I know? I know small m, which is nothing but 0.75. I know E, which is nothing but 0.5. I know omega square, where omega is 83.77. So, 83.77 whole square. I know capital M, which is 33 kg, and omega n is 100 radian per 150 radian per second. So, 150 square into h omega. So, to evaluate h omega, I would need omega by omega n and zeta. So, this 2 is going to give me h omega. So, zeta I already know as 0.05, and omega by omega n is nothing but 83.77 by 150, which is nothing but 0.558. So, if we use this 2 value, h omega is going to come as 1.45. You can see it for yourself. So, h omega is 1.45. Therefore, I can plug the value. So, plug this value of h omega here, and that is going to give me x as 5.13 millimeter. Therefore, the tail rotor will vibrate in the vertical direction with an amplitude of 5.13 millimeter. So, with this example, we end the topic of harmonic loading. I will next talk briefly about how to solve problem with periodic loading but non-harmonic. Let us move into that. So, we will be talking about periodic but non-harmonic. So, I have a loading which is periodic, that is repeating itself after certain time period, but it is non-harmonic, it is non-sinusoidal function. So, it is not a sine or a cosine function. But to know how to solve this kind of problem, we first should understand what is meant by superposition principle. So, for any linear system, when we have a linear system, one important feature of linear system is that it follows superposition principle. Suppose this is the system we have and this is the equation of motion of the system. Suppose the response of this system is u1t because when the force Ft is some particular force F1t. So, let me repeat, u1t is the response of this system because of a particular force when Ft is F1t, and u2t is the response of the system when the applied force is another force which is F2t. Okay. Now, superposition principle says that if I apply a force Ft which is a linear combination of F1t and F2t, that is, if the applied force is some constant C1 into F1t plus C2 into F2t, then the response of the system is going to be the same linear combination of u1t and u2t. So, this is called the principle of superposition. So, any linear system follows the principle of superposition, but you have to keep in mind that if you are solving nonlinear system, which we are not going to deal with in this course, this superposition principle does not hold and we cannot apply this. So, to summarize, we can say if we find out the response of a system for a given load, and let me call that response to be u1t, and if I again find out the response of the system for another load F2t and let the response be u2t, then for a third load which is nothing but the linear combination of the loads F1t and F2t, I no longer need to re-evaluate or find the response again, but rather can write the response directly as C1 u1t plus C2 u2t. This superposition principle will be of much use as we move along with in the course. So, the immediate application of the superposition principle is when you have to solve a problem when the applied load is periodic but not harmonic. Say the applied load looks something like this. So, it is a square function which is repeating itself after certain interval of time. So, this is t. So, it is repeating itself with a time period of t, but this is not a sinusoidal function. So, what are we going to do in this particular case? What we are going to do is to express this force Ft. So, this is time. We are going to express this force Ft in terms of Fourier series expansion. So, all of us know about Fourier series expansion from our engineering mathematics. So, we have to express the force Ft in terms of Fourier series, and this is the well known expression for the Fourier series expansion. So, once we expand it in Fourier series, we will see then the force get transformed into a linear combination of sines and cosine functions with different frequencies. Now, we know how to solve the system for a cosine or sine function. So, we are going to solve the system for each of the sine and cosine function, and the final response is going to be just the linear combination of this individual solution using the principle of superposition. So, at the end of this lecture, we are done with harmonic loading, as well as we know how to solve periodic functions or periodic loading, but non-periodic but non-harmonic loading. In the next lecture, we will talk about impulse loading and how to solve or analyze the system for an arbitrary loading or any generic form of loading. Thank you.